Good morning, physics fans. Welcome to another fine Monday morning at Dalton Local Virtual Learning Academy. We are close to being done. We are that close to being done. Please, if you have things that you need to turn in, please get them turned in. Get them taken care of. It's your responsibility. We have one chapter left. We're going to deal with thermodynamics. And that's the last that we will do in physics this year. So please do keep up with the material. I'm hoping to complete what I need to complete with respect to the notes this week. We will do a review and we'll do some homework, and we'll do at the beginning of next week a chapter test over thermo and over the last topic, and we will be done with the class. So today we're going to talk about what is called thermodynamics. Let me just pause 1 second here. If you go to college, I hope your weekend went well, by the way. A little chilly out there. It's supposed to be warmer this week. Yay, I'm tired of cold. I've been tired of cold for a couple months, for about 5. So hopefully the weatherman will be correct in regards to what they're predicting. If you get into college and you get into engineering or do things in regards to this, you will have to take what is called thermodynamics. They have their own book. There is actually 2 classes of thermodynamics that you have to go through. I went through them. They were a treat. They were a hoot and a holler to be able to go through. My test for thermodynamics, there was 3 classes. There was 3 different professors. Each professor would do 1 problem. And on a Friday afternoon, you had from 2 to 5 o'clock, 3 hours to complete 3 problems, 1 from each professor. Oh, what a treat that was. It was a good time. A good time had by all. Typically, the average on those tests were about a 60% was your average, and you tried to maintain. They were pretty tough. So we're going to just scratch the surface in regards to thermodynamics and what is about thermo. But we've dealt with a lot of the ideas in regards to heat transfer in the last chapter. So thermodynamics goes right along with this, the idea of heat transfer. When you're talking about a heat transfer, thermodynamics, it is a relationship between work and the heat of a system, which is thermal energy. Okay, the work of a system and thermal energy. We utilize heat and thermal energy to allow us to do work. That's thermodynamics. How can we make our job easier in machines by utilizing the heat and transferring the heat of the system into thermodynamics or into work? Let's see, power plants, nuclear power plants. The coal-driven power plants, the turbines that you have. You have so many different types of thermodynamic processes that revolve around our life that we really don't even realize. We turn on the light switch and we just think, oh, we got electricity. Or we turn on the light switch because it's too windy outside and we don't have electricity. What's wrong? There must be a line down. Well, what's the process to get the electricity to us? What's the process of making the electricity over at either Orville or down here in Masson? How do we make them? Okay, the turbines that go into that, all those ideas go into taking thermal energy and creating mechanical energy or electrical energy. Well, it's a relationship between the work and the heat of the system, which is your thermal energy. A basic example, when unscrewing a screw from a piece of wood, the screw warms up, it gets hot. Okay, if you ever taken a screw out of long screw out of a piece of wood, either by a screwdriver or a drill, you pull it out and you try to pick up the screw, you'll burn your fingers. okay, because it gets hot, okay? Where does the thermal energy come from? Well, what you have is you have friction between the metal and the screw, okay? You have the screw that's coming out of that, and then you have the friction between the wood and the screw. So what you have is you have thermal energy. The work creates the heat. The work that you did with respect to your screw, that you did to unscrew it, creates the heat, which is your thermal energy. Once placing the screw on the ground, what happens to the screw? Okay? You try to pick it up with your fingers, it gets really hot, and you go, ooh, that's hot, and you throw it onto the ground, and you let it sit for a few minutes. Eventually you walk over and you pick it up and go, oh, it's not that hot anymore. Why is that? Well, we're going back to what we did in the last chapter, assume thermal equilibrium with the environment. Okay, so it cools down, it achieves thermal equilibrium with the environment because we placed it in an environment where it's just going to cool down. It's going to cool. Why? Because the environment temperature is only 70, or over the weekend it was only 30 degrees and we saw snow. Okay, it's going to try to achieve that temperature because it's in that environment. And once again, the environment is just your surroundings. What is our surroundings? Right, today in my room, the environment is probably about 65, 66 degrees. So any object that's in here is going to try to assume that temperature of 66, 67 degrees, whatever it is. It's just our surroundings. How does a steam engine work on a choo-choo train? Okay, the choo-choo train, which was a huge mode of transportation back in the 1900s and the 1800s, late 1800s into the 1900s, the choo-choo train was able to move things, objects, peoples from one place to a second place. Okay, and it did it relatively quick compared to getting on the horse and riding a horse, where the horse got tired, or had a carriage on the back of the horse, got tired. So they invented what was called a steam engine. They put the choo-choo tracks down. Okay, how does that work? Very basic idea. What you had to begin with, you have heat and water. Okay, you heat some water. Okay, when you heat water into a boiling atmosphere, this heat creates steam. When you heat the water, and typically they did it by coal, okay? They had a coal shoveler, they had a car that they filled up with coal. And one person was always in charge of continuing to put coal into the fire and burn the coal. Well, when they burned the coal, they would heat the water. Well, when you heat the water, it becomes steam, which is heated air. Okay, so you have heated air. When air heats, hot air balloons, when it heats up, it expands and becomes less dense. It expands out. Okay, so you're expanding this air because you're heating this air. You're taking it from water into steam, which is the heated air, okay, and it expands out. When it expands the air, what starts to happen, it creates pressure. It creates pressure because if you heat up an enclosed container, it will look to try to explode. Why? Because it's being heated up. Okay, so it's going to create pressure because it's expanding out. Okay, when it expands out, what's going to happen? It's going to start moving objects. You have pistons that start to move, and this is what happens in your car also. Okay, you have pistons that start to move because the gasoline is heating air, and the air is the one driving these pistons up and down. It moves the pistons, and once you move the pistons, this starts to do work. Okay, so this heat creates this work that we have, that we're dealing with. We're starting with just water. We're boiling this water, and back in the old days, there were stop stations for choo-choo trains. Okay, they had to stop at certain stations, and they would leave passengers on and off at certain places where they look to get on and get off. But also at that station, they had to pull to an area where they were able to fill up a container full of water. They had a container that they would fill full of gallons of water so they can continue to heat the water to create steam, and it would evaporate and it would go away and it would move all these pistons, but they always had to continue to fill up with water. Not gasoline, but they had to fill up with water. And that was at the train depots that they used to have. They used to stop at those places, and they would leave passengers on, or passengers would come off, but they had to pull ahead to an area where they could pull a handle down, and they could fill up with the water, and they could refill up with water, and they create the steam again. How can work be changed into thermal energy, or thermal energy can be changed into work? Okay, it goes both ways here. It goes both ways. Heat and work are just in transit. Okay, they go from one to the other, back to one, back to the other. Heat will create the work. Work will create heat. Okay, so your friction from work will create heat. Okay, the heat will create pistons that move, that will create the work. So like for your cars, okay, how your car heats, initially how it starts to warm up. When it's cold, you turn on the register or the little dial down there, and you want to heat up the car real quickly, and it's 30 degrees outside. Well, cold air starts to come out to begin with. Well, hot air doesn't start coming out until the engine starts to warm. When the engine starts to warm, we utilize that heat to be able to heat the car, the interior of the car. So the heat is a byproduct of the engine, but it's also used to heat your car. Okay, if your car is really hot. I mean, if your car warms up and it's the middle of winter, the car warms up, you're driving a lot of distance, and you come home and you park it in the garage, and you close the garage door. Well, it's cold outside. What will happen is the heat will come off the engine of the car and it will cool. Okay, but the heat has to go somewhere. Where it goes, it just doesn't evaporate. It goes into warming up your garage. So in the middle of winter, it's good when you want to heat, or when you want to try to save heat in your house, because your garage is like an insulator. You come home, you park your car in your garage, and you close the garage door right away, because what that will do is that will start to warm up the garage. And the garage then will help try to keep your house insulated, because it is a vast area that's connected to your house. So if you don't have good insulation, that's how you can warm your house a little bit. When we talk about a system is a set of particles or components that work together to do a task. Okay? A system is a set of particles or components that work together to do a task. Our bodies are systems. Okay? There's a bunch of systems in our body. If we start taking out part of our systems, we start running into problems. If we take out our kidneys, okay, our body will start having problems functioning, because we don't have kidneys to filter our blood. Okay, obviously if you take out your heart, that's a big issue. So if we start removing components, we start losing efficiency of our body, basically. If you have a health thing that you lose capacity in a lung and you only have one lung, it's tough for you to go out and run a marathon. It's not undoable, but it's tougher to do because your capacity of your lungs diminish. Cars are systems. Okay, if you take out certain systems of your car, it's going to have issues. Okay? If you take out the radiator fluid, or just the radiator that keeps your car from warming too much, you're going to have issues because your car, the components, the engines of the car will heat up to 200 degrees. And if you have 200 degrees there and you're not able to cool the engine, your engine will start to break down because it's going to get too hot. So these are systems. Here we have gas, some air. You have air in here, and you have a piston. Okay, you have a plunger that pushes down. You have a distance. You have this distance, or the plunger that gets pushed up. You have this distance that gets pushed up. You have a cross-sectional area that you're dealing with here. How is pressure calculated? Pressure is force times divided by area. Force divided by area, sorry. And when you're talking about this piston, what you have is you have this piston here, and you have just the plain old atmosphere that's just holding it in a certain area. Well, if I talk about my pressure is equal to force, the force that's being exerted here per unit area. And how is work calculated? Work is your force times your distance. So when we have work as force times distance, we have pressure is equal to force divided by area. If the piston is filled with air and heated, okay, so you have this air here, and you have this plunger down at this point, and it's heated. So it's going to, once again, the gas is going to expand when it's heated. Okay, the gas will expand when it's heated, and it's going to push the plunger upwards. Your change in volume, your change in your volume that you're dealing with here is this area, is basically a cylinder, this area times this height, or this distance. It's the volume of a cylinder. So this change in the volume, the piston is filled with air and heated. What's the change in the volume? That's your area, your cross-sectional area, times your distance. You're just calculating the area or volume of a cylinder. Well, if we take a look at what would be the equation to calculate the work done by the gas, assume the pressure remains constant, and the outside pressure is not changing. Your work is still your force times your distance. But if I use some mathematics and multiply my top and bottom by my area, okay? We can multiply by the value of 1. What we're going to do is we're going to look to manipulate this and move this area around. So I'm going to take the area, this area here, that's on the bottom, and move it over the force. And then we have our distance times our area still there. Well, force divided by area is equal to pressure. It's equal to the pressure from up above. And this distance times this area is equal to our change in volume. Okay, which is what we have here. Area times our distance equal to change in volume. Our force divided by area is equal to our pressure. So the work is equal to the pressure times our change in volume. And once again, this is true only if we have a constant pressure. We're not changing our pressure from up above. if our change in volume is positive, okay, what is doing the work? Well, the gases. We're heating up the gas, and it's doing work for us. Once again, we're taking thermal energy, which is just heating gas. We're just heating the gas, and we're increasing the volume. When we increase that volume, we start to do work. Why? Because this piston will move upwards. So the gas is doing the work. And all we had to do is we had to supply a heat source. We had to put a candle, a burner, or something underneath it just to expand the gas. If delta V is negative, okay, which means I'm losing volume, what's doing the work? Well, what's doing the work is now the piston, or the atmospheric pressure. I may have put my hand on top of that piston and started pushing it downwards. Okay, so I'm now doing work by the atmosphere or the outside atmosphere. And once again, if delta V is 0, there's no work being done. I'm not changing my volume at all, so I'm not doing any work. So because the piston's not moving. So once again, thermodynamics, what thermo is how can we utilize heat, or how can we utilize systems to be able to create work for us? Okay, that's what we want to be able to do, is we want to be able to use a system, and a lot of times it's a lot of thermal energy. We want to use this thermal energy to be able to create work for us. Okay, because it's an easy thing, because we're talking about fire. Okay, we're talking about fire, we're talking about maybe a nuclear reaction. When you have a nuclear reaction, you create a lot of energy and a lot of heat. Well, a lot of that energy and heat, what it's doing is boiling water, creating steam. If you ever drive past a nuclear power plant, okay, you have this circular thing here, and you see this bellows, just bellows of steam coming out of it. What that is you're having nuclear reactions that are heating water. And when you start heating water, you're able to start creating your energy, and you're able to create electrical power at that point. Okay, you go down to, or over Orville, they have a coal power plant, and over in Massillon, they have coal. I used to work at the power plant over in Orville, and they used to have semi after semi of coal that used to come in that they would burn to be able to generate their work for their turbines, to be able to generate your electricity. Okay, so there's many types of heat sources that are out there. They're trying to do away from the coal, because coal tends to add a lot of pollutants to the air. The fossil fuels, they will create a lot of pollutants. The gasolines, they'll create a lot of pollutants. In your car, your gasoline, what happens to your gasoline? Well, you have spark plugs in your car, and the spark plugs will create a little spark, and it will ignite the vapors of the gasoline. And when you ignite the vapors of the gasoline, once again, you're creating heat. And when you create heat, you're heating air. And when you heat air, you start moving things. And when you move those things, you start generating your tires moving at that point. So there's a lot of systems that are out there that are utilized to be able to create this heat, to be able to make things move. Like I said, car engines are huge, to be able to move pistons in a car engine, because those pistons that move will eventually make your wheels move. Okay, so that is, once again, just another system. We will continue on with thermodynamics throughout the week here. Once again, this is the last thing that we're going to cover in this in this class. So we will be dealing with thermodynamics the rest of this week. Look for an evaluation or chapter test over this either at the end of this week or the beginning of next week. I'll probably get it to the beginning of next week, and that will be the last thing that we will cover then. Keep up with the material. Once again, please do keep up with the material. If you have any questions, feel free to ask. Other than that, adios. I miss you guys. See you tomorrow.